Suppose we are given two series, summation an, summation bn, and summation an converges to a and summation bn converges to b. Then does it make sense to take the product? Is there a natural product on this? Well, naively, you would think that we can consider the product summation a and bn. Does this converge? Does this converge always? Well, let's take an example. Suppose I take an to be equal to bn to be equal to minus 1 power n by square root of n. Then summation an converges. Think about why this is the case. In fact, we have got a precise test that sort of tells you why this converges. Then summation a and bn is nothing but summation minus 1 power n by root n into minus 1 power n by root n, which is just summation 1 by n, which diverges. Okay, so it's not always the case that if you take a series of the form summation an and another series of the form summation bn and naively take the product summation a and bn, that need not converge. Let's try to take a more refined product. Okay, what we do is the following. Observe that the terms can be written like this: a1 plus a2 plus dot 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 times b1 plus b2 plus dot dot dot. Then rather than taking this series summation a and b and this product naturally by distributivity looks like a1 b1 plus a2 b1 plus a1 b2 plus a2 b2 plus a3 b1 plus a1 b3, so on. I can write this product sort of by simply manipulating it algebraically without worrying about issues like convergence and validity. I can write it as summation Cn, where Cn is summation k running from 1 to small n a k bn minus k. That means I'm grouping together all the terms from ai and bi, ai and bj, such that I plus j is actually equal to n. That's how I'm grouping the terms together. This produces this Cn. Okay, so this each Cn is actually just summation k equals 1 to n a k bn minus k. So this is a different product than this naive product summation a and bn. This is called the Cauchy product. This is called the Cauchy product of the two series. So more precisely, this formula is the formula for the Cauchy product. Okay, now the question arises, does the Cauchy product converge? Does the Cauchy product converge? Okay, in other words, what is summation Cn? Okay, now I'm going to prove a very simple result. This is not the most general result on these lines, but it's more than sufficient for our purposes. Theorem. I believe this is due to Mertens, but I think what Mertens proved is a more general result. What I'm about to prove is much simpler. It was probably known much before Mertens. Suppose summation an and summation bn both converge absolutely. Okay, call this a, call this b. Say summation an converges to a, summation bn converges to b, both converge absolutely. Then summation Cn is just, as you can guess, ab. And this convergence is absolute, and this convergence is absolute. Let's see a proof. And the proof is not very hard because I am assuming both series converge absolutely. Suppose summation mod an is equal to alpha and summation mod bn is equal to beta. The aim is to show that summation Cn converges absolutely. That's the first claim in this theorem. Now, how are you going to show that summation Cn converges absolutely? Well, observe the following. Look at summation mod Cn n running from 1 to capital N. Okay. Now, this will consist of terms that look like this. Mod a1 b1 plus modulus of a1 b2 plus a2 b1 plus so on. Various terms. This is certainly going to be less than or equal to summation I plus j less than or equal to capital N mod ai mod bj. Right? I have just applied the triangle inequality to the various terms in the previous sentence. Now, here is the catch. This is in fact less than or equal to mod a1 plus mod an times mod b1 plus mod bn. Notice that all the terms in this expression, after you have expanded it out using distributivity, all the terms here will be of the form mod ai bj, but with the possibility that I plus j could exceed n. Okay, so I must be precise. I put a capital N, that makes no sense. It should be, I put a small n, it should be capital N. It should be capital N. Okay, so every term that occurs here is of the form ai bj, but I plus j could be greater than or equal to n, could be greater than n. Therefore, you have this inequality that summation I plus j less than or equal to n mod ai bj is less than or equal to this product, and this is certainly less than or equal to alpha beta, because that's what summation mod ai and summation mod bi converge to. Okay, so what this shows is that the partial sums of summation mod Cn is bounded by monotone convergence theorem. We are done. We have shown the absolute convergence of summation mod Cn. Now let's go to the second part where we have to show that summation Cn actually is equal to AB, and here the trick is not that different. What we do is we consider summation n equals 1 to 2n of Cn minus a1 plus a capital N times b1 plus b2 plus b capital N. Let's look at this difference. If you think about this difference for a couple of minutes, you will notice that there will be plenty of cancellations, and the only terms that will be left behind are those of the form ai bj, where at least one of I or j is greater than 2n. So let's write that down. We perform all these cancellations and then apply the triangle inequality, and you can see within a few minutes of thought that what you will be left with is this quantity. Summation I equals capital N plus 1 to 2n minus 1 summation j running from 1 to 2n minus I mod ai mod bj plus mod bi mod aj. Okay, so these are all the terms of the form ai bj where one of the indices is at least n plus 1, and after applying triangle inequality I have written it down as summation I equal to capital N plus 1 to 2n minus 1 summation j equal to 1 to 2n minus I mod ai bj plus mod bi aj. So if you understand this step, the rest of the proof is fairly easy. Now what I do is every occurrence of mod bj in this first term I replace by beta, and every occurrence of mod aj in this second term I replace by alpha. So I get this to be less than or equal to summation I equals n plus 1 to 2n minus 1 mod ai beta plus mod bi alpha. Just to ensure that it is clear that the summation is over both quantities, let me just put parenthesis. Okay. Now, simplifying again, this is less than or equal to summation I equals n plus 1. I won't go all the way to 2n minus 1. I'll go all the way to infinity. So, of mod ai beta plus summation I equals n plus 1 to infinity alpha times mod bi. Okay. Now, both of these quantities are tails of a convergent series. Both quantities are tails of a convergent series. This means that both terms summation I equals n plus 1 to infinity mod ai and summation I equal to 1 n plus 1 to infinity mod bi, both of these converge to 0 as n goes to infinity, being the tails of a convergent series. This just means that limit n going to infinity of summation n equals 1 to 2n of Cn is equal to limit n going to infinity of a1 plus dot 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 an, a capital N times b1 plus dot 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 b capital N. And this we know is equal to ab. Okay, so this concludes the proof. So the second part is a bit tricky, but not really difficult. Just go through the proof once or twice, look through the notes also, and make sure you understand which terms cancel and what terms we are left with. And indeed, we have that limit capital N going to infinity, n equals 1 to 2n, Cn is in fact equal to ab. Okay, now let me just make one remark, just one remark. So we have assumed both an and bn are absolutely convergent. This is just for simplicity. It actually suffices if one of them is absolutely convergent. The other needs to be just convergent. I am not going to prove this more general result. This result that I have stated and proved is usually sufficient for most of analysis, but it's good to know that there is a more general statement available which you can read up on your own. This is a course on real analysis, and you have just watched a module on the Cauchy product.